Thank you for attending the 2021 CPES conference. My name is Min No, a second year's master's student at CPES. I received my bachelor's degree in electrical engineering from Virginia Tech in 2019. I joined CPES in fall 2019 and my advisor is Dr. Dong Dong. My research interests include high-frequency magnetics, thermal modeling for transformers, transformer characterization, and cooling system design for power electronics. In order to meet the high power density demands of the future, CPES is now conducting extensive research on high-frequency magnetic components. Today, I'll be talking about a 500 kHz, 18 kilowatt solid-state Litz wire transformer, which uses a newly developed winding technique called Intra-Leaving. The designed transformer achieves low leakage inductance, high efficiency, high power density, and equal current sharing among parallel windings. This work was sponsored by Power America. For further details on the resonant converter circuit design, please see my partner Yulian Kal's presentation. As the transportation industry moves towards a more fuel-efficient and renewable future, there have been increased calls for development of high-power density, low-profile battery charging solutions. For electric powertrains, weight and size are key factors alongside efficiency. Here at CPES, we developed an 18 kilowatt, 500 kilohertz bidirectional battery charger that operates with a majority power path and a minority power path. The minority power path acts as a voltage regulation stage, but because it acts as a minority power path, power loss on the regulator is low and a peak efficiency of 98.8% is achieved. Please see the presentation by my partner Yulian Kal for more details on the circuit design. The converter features two transformers, 8-to-4 and 10-to-1, made with Litz wire and a total power density of 140 watts per inches cubed. One of the key design targets for the proposed converter was for both transformers to have low leakage inductance. Because the converter operates at a fixed resonant frequency, flat unity gain is desired to reduce gain variance around the resonant frequency. This is achieved by having a large ratio between the leakage and magnetizing inductance. An extensive winding topology survey focusing on low leakage inductance, high efficiency, and power density was conducted, and we finally settled on the transformer design shown on the bottom right hand of the screen. An 18 kilowatt, 500 kilohertz intra-leaved transformer with low primary and secondary leakage inductance of 747 nanohenries and 120 nanohenries respectively. Low leakage inductance is achieved by the selected PS-PS layering structure, where the secondary is composed of two parallel secondaries. Parallel secondaries were employed to lower Litz wire current rating, to lower system copper costs, and also improve winding fill factor, leading to a high power density design. The transformer features potted winding to improve heat spreading, embedded thermocouples for internal temperature sensing, and a power density of 1700 watts per inches cubed. On the next slide, we will further discuss this coin we term intra-leaving. Originally, our winding topology survey led to a PS-PS design, which you see on the top left of the screen as the design with the highest efficiency and lowest leakage inductance. The primary side carries 28 amps RMS, and the secondary side carries 56 amps RMS. All windings, though, primary, secondary 1, and secondary 2, now each carry 28 amps RMS because we use parallel secondaries. This allows for the same gauge Litz wire to be used for all windings. The design has one major drawback, however. Because of the geometric mismatch between parallel windings S1 and S2, the two windings have an impedance mismatch. The leakage inductance of secondary 1 is smaller than that of the leakage inductance of secondary 2. As a result, the current sharing between the two windings is atrocious, with S1 taking the majority of the current, over 75%. For high-frequency SST, geometric mismatch is especially a challenge because any small variation in leakage inductance between parallel windings will be significantly amplified by the high operating frequency. Current sharing imbalance is dangerous for long-term operations since secondary 1 will be taking more current than the Litz wire is rated for, increasing the risk of thermal runaway. To fix this, we propose a winding structure we are coining as intra-leaving. Intra-leaving means alternating between two groups, primary and secondary, but intra-leaving means not only alternating between your two major groups, primary and secondary, but also alternating within a group. In this case, we alternate within the secondary winding group. With every turn, the positions of secondary 1 and secondary 2 are interchanged in space. As shown in the slide, we take 2 turns from each layer of S1 and interchange it with 2 turns from S2. By doing this, we get a good impedance match between parallel windings, S1 and S2, because in reference to the primary, they now share equal positions in space. Current sharing results with and without interleaving are shown on the right-hand side of the screen. With intra-leaving, we achieve an almost perfect current sharing distribution, with S1 taking 53% of the current and S2 taking 47% of the current. The final part of this work was developing a simple and easy-to-use core loss measurement method. State-of-the-art core loss measurement techniques for AC waveforms are time-consuming to use, vulnerable to system parasitics, and prone to measurement error due to AC resistance loss. And furthermore, they only report a loss per unit volume. Our core loss measurement technique focuses on two simple-to-use tests, where in the first test, the core under test, the cut, is set with a large magnetizing inductance. And inductor in parallel with the cut is used to achieve ZVS for the excitation circuit. By doing this, we minimize error due to AC resistance since the magnetizing current to the cut is small. The second test removes the core under test and runs with only the parallel inductor used during the first test as the load to the excitation circuit. Core loss is then simply calculated as the power difference between two tests, since the presence of the core under test is the only thing to change between the two tests. Because the inductor L is used to achieve ZVS, switching loss is negligible, and only conduction loss needs to be accounted for, which is easy to do. Furthermore, since the magnetizing inductance of the core under test is large, error due to AC resistance is small. And finally, this method does not require reactive compensation like other core loss measurement methods, making it applicable for a wide range of AC waveforms.
During the presentation, we showed you the final version of the Intra-Leaved transformer, which I'm holding right now. Before we look at the final version, I want to first show you an unpotted version so we can look at the winding structure. During the actual winding process, we make the winding structure as tight as possible to reduce leakage inductance. For the purpose of this demonstration though, I over-exaggerated the winding a bit to clearly show off the intra-leaf structure. Moving from top to bottom, the layers are primary 1, secondary 1, primary 1 again, and then secondary 2. The two primary layers are in series, and the two secondary layers are in parallel, giving us a well-interleaved structure to reduce leakage inductance. Here, I removed the intra-leaf secondary to clearly show you the winding strategy. To improve current sharing, here you can see where we've swapped the position of secondary 1 and secondary 2 marked in black. We do this swap after every turn to make sure the impedance of the two windings are well matched, which will yield equitable current sharing. Here, we have the final version where we have potted the winding in thermal epoxy to improve heat spreading in the winding bundle. We can compare its dimensions to a Samsung S7 to really show off our high power density design. 18 kilowatts through such a small, thermally stable transformer. Please see my second presentation of this conference for the thermal design details of this transformer. The last thing I want to show is a test setup for the core loss measurement method technique I discussed during the last slide of my presentation. Our test setup is very simple, which is the benefit of our technique. We have a full bridge converter, our core under test, and another transformer which we are using as an inductor to provide ZVS. The only other pieces of equipment you'll need are a DC power supply, an oscilloscope, and a few probes to measure current and voltage. As you can see, the test setup is really simple compared to other techniques which require power amplifiers, calorimeters, sensitive shunt resistors, or components for reactive compensation. Furthermore, this method is very resilient against system parasitics, so you don't have to worry about those interfering with your core loss measurement. So here's our test setup with our full bridge converter, which is connected to a DC power supply. We have our core under test right here, and here's our transformer, which is acting as the parallel inductor to provide ZVS. The key to this method is ensuring that the core under test has a very large magnetizing inductance relative to the parallel inductor. And doing so is very easy to achieve by adjusting the air gap. For example, your core under test could have no air gap for a large magnetizing inductance, and your parallel inductor can have a few millimeter air gap for a small magnetizing inductance. A factor of 2 between the two inductances is more than enough. So during the first step, you're going to turn everything on with your two transformers parallel at the output and run the whole system until a thermal steady state. Once that point has been met, we'll collect the DC input voltage and the current coming out of the power supply, which you can easily measure yourself or just read the value off your power supply screen. Here on the oscilloscope are waveforms from this test. We have the gate still at the top, VDS of the full bridge in the middle, and the magnetizing current going through the parallel inductor. The second step, because remember this is a two-test process, is to remove the core under test and only leave the parallel inductor connected. This is the one with the small magnetizing inductance. We rerun the same test, no excitation changes, nothing changes except for the fact that we removed the core under test. Once the system reaches thermal steady state, we collect our DC input voltage and DC current measurement. On the oscilloscope is the waveform for our second test. Notice how there is very little change in the magnetizing current between these two tests. The magnetizing current RMS only differs by 0.2 amps, which means that a very small amount of current flows through the core under test, which helps minimize error due to RAC loss. Now that both tests are done, the loss of the core under test is very simply the power difference between those two tests, since the only thing that changed was us removing the core under test and nothing has changed in our switching network. The parallel inductor achieves SAW switching, so the only loss on the switching network is conduction loss, which can be easily found through a datasheet. Today, we looked at a high-density, 18 kilowatt, 500 kHz transformer with the novel Intra-Leaved winding structure. The winding structure allows us to achieve balanced current sharing among parallel Litz wire layers. The Intra-Leaved structure also achieves low leakage inductance for the primary and secondary, 747 nanohenries and 120 nanohenries respectively. The transformer winding is potted in thermal epoxy to improve heat spreading, and the whole transformer has a size profile similar to that of an iPhone 5, achieving a power density of 1,720 watts per inches cubed. This solution has 3 times higher power density than commercial solutions with remarkable thermal performance. Please see my other presentation for more details on thermal results. Finally, this work also proposed a novel core loss measurement method that is fast, easy to use, and has minimal equipment requirements. Thank you for attending the CPES conference.